All right. Welcome,
Right.
everyone. We're very happy to have Jamie Patton here to talk about nutrient management and soil health assessments in reduced tillage systems. And Jamie's going to start us off with a presentation. Welcome, Jamie.
Thank you very much,
Anytime you're
Claire.
ready.
All right. So I'm very informal. So if you have questions, pop them into the chat and we will move forward. So I'm really excited to join you today. I apologize. I am in a hotel room. This looks like my internet's going to hold. So I'm down in La Crosse, thankfully, where it's just raining and rather than icing and snowing like the rest of you. So for those of you who don't know me, my name's Jamie Patton, and I'm an outreach specialist with the Nutrient and Pest Management Program. What that means is I get the pleasure of talking with people all the time. And most of the time I'm talking to people from the bottom of a soil pit. So I have 2 soils degrees, one from Iowa State and one from Oklahoma State. So I put a little map over to the side. Ruth said you might want to know a little bit more about me. So I was born and raised in Iowa. And like I said, I had my schooling in Iowa and Oklahoma. From there, we moved to Missouri, and now we live up near Green Bay, Wisconsin. So been a little bit over the Midwest. You'll see a bunch of other stars on that map, and those are places where I've done soils research for my degree. So a little bit from the Oklahoma Panhandle, working in those very dry environments out in Texas County, looking at those beautiful calcareous soils out there, as well as with Amish farmers across the central Midwest. So a little bit about me. I have a husband and a son, and so we oftentimes, as you'll see from the picture at the bottom, we leave my husband at home. He's not adventurous, and my son and I go out and see what we can do with waterfalls in the northern part of the state. So just a little bit about me. My passion really is soil, and usually I'm talking very excitedly about soil aggregates, and you can see that from that picture down there. So soil health really is my passion, and how we can manage soils as individuals to help us with our production goals. So today we're going to talk about that kind of from a nutrient management lens from the very beginning. So we're going to dive just a little bit into soil chemistry. So we have an hour. And we have a lot of great questions that Rue posed to me. So those will come at the end, but just kind of set us up with some of the background in soil chemistry. So as we remember, and when we manage nutrients, oftentimes we focus on NP and K, nitrogen, phosphorus, and potassium, but we really do need to remember that there are 18 essential nutrients for plant growth. We can argue about cobalt, so some people will say 17, but I say 18 essential nutrients for plant growth. And of those, 15 come from the soil. So I have let all the chemistry down at the bottom. So I like to look at this saying, and so if you're looking why I spaced it out the way I did, it is, so a little mnemonic here, C. Hopkins Cafe, managed by my cousin Mo Nickel. So again, remember I was trained in the South. So C. Hopkins Cafe, managed by my cousin Mo Nickel. And so what this does is this little mnemonic separates out our nutrients into the macronutrients, the micronutrients, and it separates out those that do not come from the soil. So carbon, hydrogen, and oxygen, the first 3, we're going to see that our plants get those from air and water. So oftentimes we're not thinking about managing them unless we're in a greenhouse. We may be adding some carbon dioxide to get the plants up and growing, but we don't think about those in field systems other than we need water, but not from a nutrient standpoint. Then we look at the rest of the nutrients, and you'll see the ones in pink we consider macronutrients, and the ones in gray we consider micronutrients. Those macronutrients are just needed in larger amounts than the micronutrients. So it's not that they're more important, it's simply that they're needed in larger amounts. And so that's why we manage nitrogen, phosphorus, and potassium, because they're often deficient in our soils because they're needed in such great amounts. There's also calcium, magnesium, and sulfur. And so for those of you in the state of Wisconsin, I will argue that we really need to, if you're not already, pay attention to that sulfur because it's very commonly deficient in many of our soils. The micronutrients are then listed after that. And some of us may actively manage those micronutrients and some of us may not, depending upon our organic matter levels as well as our soil texture. So some of us in those sandier soils, low organic matter soils, need to be thinking about those and potentially supplementing those later on. And we'll talk about how we can test for those and think about those and whether or not we need those in our add into our system. So I would be remiss if I talked about soil chemistry as well as soil fertility and didn't mention soil pH. So when you talk to most soil scientists, they're going to talk to you about how the one soil property that maybe is the most important, that controls, biology and chemistry in the soil, they're going to tell you it's pH. And it's up for debate, but I would be remiss if I didn't talk about it, particularly when we talk about soil fertility. So soil pH is going to control which form of a nutrient we have in a soil. So even though we may have a nutrient in the soil, the plants only take up specific forms, typically those inorganic nutrients. And so you'll see those listed on the right-hand side, the specific form of a nutrient taken up by the plant. And why this is important, particularly in soils as we look across the Midwest, particularly, and I'm most familiar up here with Wisconsin, some of our soils have pHs well above 8. Some of our soils have pHs. I've actually ran into one that was down close to 3. So we run this entire gamut of pH, and as we change pH, we're going to see that chemistry is going to change the form of the nutrient that's going to be available to the plant. And so what the chart is showing on the left-hand side is the availability of a particular nutrient at a certain pH. So when the bars are very, very wide, that means that that nutrient is more available. And when the bars narrow down, that means that that nutrient in particular is less available. And this is why soil science is so fun, is because it's a balancing act. So when we look at those macronutrients, the nitrogen, phosphorus, potassium, sulfur, calcium, magnesium, the one on the top, you'll notice that those bars tend to get wider as that pH increases. So as we go from 6 to 7 to 8, you'll notice they stay nice and wide, and those nutrients stay nice and available. It's when the pH drops below that pH range of 6 that the nutrients become less available. On the opposite ends of the spectrum, we'll see iron, manganese, boron, copper, zinc, many of the micronutrients. They tend to be more available at those lower pHs, and they tend to be less available at the higher pHs. So when we talk about soil fertility, the first thing I always ask people is, do you have a soil test? Do you know what your pH is? Because if we want to start looking at amendments, and we want to even look at soil health and how we can manage and promote biology in our soil, we need to know that pH. And the ideal range for most crops that we're growing is going to be in that pH range between about 6.5. Legumes may be a little bit higher, but in that 6 to 6.5. And the reason for that is, you notice that is where those bars are maximized both for the macronutrients and the micronutrients. So we always start with pH. Then we move on to the rest of the soil fertility, right? And we'll talk about, we go out and we take soil tests, right? And so most of us will use that basic soil test. We go out, we take that composite sample, we send it into a laboratory, and it tells us what nutrients are going to be available over the next few years for our crops, particularly P and K, and if we order them, some of our macros and micros. And I want to remind you, there's so many new soil tests coming out onto the market that I want to remind us how soil testing actually works. So there's basically 3 steps to developing a soil test. First, we have to do extensive research, right? So there's thousands of site years of data that goes into making nutrient recommendations, and they're going to be calibrated for specific regions, specific soils. So you'll notice Iowa's recommendations are not the same as Wisconsin or Illinois or Missouri's. You'll notice, even depending when you get in the state, the recommendations for me up in Green Bay are very different than those down in Dane County, depending upon soil type. So we really need to know that that soil test is going to replicate and identify the nutrient needs and application rates that are going to optimize plant growth and economics and environmental productivity within that given region. So they're based upon an extraction, which is basically a chemical method that measures that available pool. But more importantly, that extraction, the number generated by that extraction, is going to identify the relationship between the amount extracted and the amount that the plant needs. And this is how we come up with those soil test levels: very low, low, optimum, high, very high, high, right? So all of that, that's how they're correlated there. And then once we have that identification, then calibrate it with the amount of nutrient that we need to apply in order to reach that critical level that optimizes plant growth. And the reason I point this out, and again, it's very quickly in this very short presentation, is we get really excited about some of these new tests, but we need to recognize that they are still in the correlation and calibration standpoint of these soil test recommendations, and we're not ready to use them yet in many parts of the state. So while there's new and exciting prospects out there, we are, and as a nutrient management planner in the state of Wisconsin, I cannot use those yet to write you a DATCAP approved nutrient management plan because they haven't gone through this rigorous procedure to calibrate and correlate. Okay. And we'll talk more about that. So there may be some questions about, for example, the Haney test and why we have difficulties using that in the state of Wisconsin because it hasn't gone through all 3 steps yet. So if you're in the state of Wisconsin, our soil fertility information is all contained in A2809. That's an extension publication. And as you can see, nutrient application guidelines for field vegetable and fruit crops in Wisconsin. So it's a very thick book. It contains an incredible amount of information, and everything you need to know is in here. I also recommend if you're having insomnia, this is also a really good book to start reading from the beginning to the end. No, I'm teasing. So it's really hard to do this on Zoom, right? So if you've ever tried to read it, it's a pretty rough read, but it is an excellent resource for us in soil fertility management. But that's just the real quick basics of soil chemistry. Where I really get excited, and that's where I feel bad watching myself on Zoom because I talk a lot with my hands, right? But where it really gets exciting, right, is where we start to talk about getting to those plants to the nutrient, right? And this is where soil health comes into play. So I can argue all day long, and it's actually fairly straightforward and fairly simple. The science is there. I take a soil test. It tells me how much I need to apply. I can apply that nutrient. Very simple, very basic. But can the plant get to it? And this is where I would argue, from standing in soil pits from all across the nation and standing in hundreds of pits in the state of Wisconsin, I would argue this is where we have the issue. So whenever I get in a soil pit there, I haven't been in one yet where I don't see compaction, right? And so as soon as the soil becomes compacted, we have difficulty getting roots and that symbiotic fungi out there exploring that soil to find that nutrient and take it up. So arguably, a lot of our issues are with nutrient acquisition, not nutrient supply. And why this is important is when we think about how plants take up nutrients, there's basically 3 ways, right? There's mass flow, and that's what the diagram on the left-hand side is showing us. There's mass flow. And what that means is that the nutrient is dissolved in water, and it's moving with that water to the plant root. So as that root takes up water and is moving through the plant, as the plant transpires, right, that nutrient is moving with that water. And why that's important to us is nutrients that are taken up primarily by mass flow, and you can see those in the table on the right-hand side, nitrogen, for example. Placement of that nitrogen is not as, the sensitivity of that plant to the placement of that nitrogen maybe isn't as great because that nitrogen can move around with that water in the system. And so that is a really important factor for nitrogen. When we look at our other nutrients, for example, look at phosphorus and potassium, you'll see that it's primarily taken up by diffusion. And what that means is that the root has to almost come in contact with that nutrient. That nutrient is going to move due to differences in concentration. It moves from high concentration to low concentration, and it's only going to move a few millimeters in the soil. So basically, the root almost has to come in contact with that nutrient in order to take it up. And so that means anytime I have a stunted root system, because of cold, wet conditions, you'll see that phosphorus deficiency showing up in that picture in the lower right-hand corner. That phosphorus deficiency shows up as that purpling of those lower leaves. That is oftentimes in the springtime due to, not because the phosphorus isn't there, it's due to that stunted root system and the plant simply can't get to it. And if you called me out and said, what do I do? I'm going to say, wait. Let the soil warm up, let the conditions change, and let's see if this deficiency disappears. And oftentimes, if it is a cool, wet soil, then it will. If it doesn't, then we need to address it. I see Dylan's raised his hand.
Yeah, I was just wondering if you know of data for micronutrients for like this, thinking about mass flow versus diffusion and accessing it.
So many of them are going to move due to diffusion. So there's actually fairly low concentrations. I believe, I don't think about this very often because we're managing those other nutrients. I believe boron, because when we think about it, it's an anion. So oftentimes, let's go back to this one, and I got to move your pictures out of my way here. So when we look at that uptake form, typically nutrients that move via mass flow are going to be anions. meaning that they're negatively charged. And the reason for that is, remember that our soils themselves are negatively charged. So nutrients that are negatively charged can't be attracted, right, to those cation exchange sites. And they're going to be more out in the soil water, and they're going to be more moving around in that soil system. So things such as nitrogen, such as sulfur, so you see that sulfate. Phosphorus is the exception to that rule. So that phosphate doesn't move very far, even though it's an anion. So we're going to think oftentimes, in general, the anions are going to move via mass flow, while others are going to be moving by diffusion. You'll notice that in the chart is talked about mass flow, calcium and magnesium, right? Why do they move by mass flow? Simply because there's large amounts of them in the soil, right? So we have very large amounts of calcium, magnesium. They're not all on the cation exchange sites. They're not all being held by the soil. Therefore, they're out in the soil water, and they're going to move with that water to that root. So again, when we think about many of those micros, you'll notice many of them are positively charged. And so we're going to think about them being attracted to cation exchange sites, right, and see less movement. Plus, they're often found in lower concentrations, so they're not going to be as prolific out in the soil water, and are not going to move as well by mass flow. Realize all nutrients move by all three mechanisms. This is the dominant form of movement that we think of plants accessing those nutrients. Did that make any sense, Dylan? It's been a long week. It's been a long week. It still feels like Friday. I'll be honest. So if it doesn't make sense, just let me know. And if for any of you, if none of this is making sense, just raise your hand, holler at me, and we'll take a step back and think about it. So like I said, we're getting a chemistry class here in about 40 minutes. So, but like I said, we can talk about that, and that's a little bit easier. But when we talk about soil health, so everybody else, right, is being moved by diffusion. And so that's why it's so important, when we think from a soil health standpoint and from a nutrient acquisition standpoint, that we have to get roots out there, roots everywhere. The more roots we have in the system, the better ability we are to access those nutrients. So in general, when you look at the research, they're going to say that compaction is going to reduce our yields somewhere between about 25 and 50%, depending upon, or more, depending upon the severity of that compaction. And it has to do with waterlogging. It has to do with access to air, but it has to do with access to water. And like I said, yeah, Rue. Are you?
Yeah. Jamie, I just wanted to highlight a couple of questions in the chat that might be relevant now as well, about nutrient uptake through fungal symbiosis. Thomas particularly asked about whether it helps with movement of P or K through diffusion, and Liana asked whether nutrient uptake via fungal symbiosis has been studied enough to know how much, like what fraction of nutrients are plant available via fungi.
Two excellent questions. So there has been quite a bit of research on the symbiotic fungi and their role in nutrient uptake. We know in particular is they're going to be impacted by the concentration of nutrient in the soil themselves. So it's much like rhizobium. So if you ever think about nitrogen fixing bacteria, when you talk to us soil geeks, we're going to tell you, right, if there's nitrogen in the system, rhizobium are going to be lazy, and they're not going to fix nitrogen. So you're not going to get as much free nitrogen through that fixation process, because the rhizobium are simply going to use the nitrogen that's already there. Kind of a similar thing with this fungi. So if we have soils that are nutrient rich, we tend to get less symbiotic fungi activity and relationship and infection of that plant by those symbiotic bacteria, and we'll get less nutrient uptake by those fungus. But I believe, and so don't quote me on this, it is a very, very large percentage, and I should have put that, I have these in other slides, but not these, like 70% of the phosphorus and potassium may be taken up by that fungi rather than the root system, and transferred over to that plant. It's a double-digit number of nitrogen as well. I'm trying to remember my slides. Is it like 20 to 40%? Like I said, don't quote me. Quarter. And many of these micronutrients, because they're found in the nooks and crannies inside those aggregates throughout the soil system, that fungus, as it proliferates, those soil aggregates are able to access that and get into those teeny tiny spaces where these nutrients are stored and take those up. So we're talking double-digit percentages. A significant amount of nutrient is actually taken up by that fungi. I actually read once, I was looking for numbers, and in one study, it was saying maybe somewhere up to, right, 700%. So fungi increase the surface area of that root system by up to 700%. So that is incredible when you think about that. You know, we get our root system is 7 times bigger with the fungus than it is without. And I love to think about that and the role of that fungus, right, in this nutrient acquisition. Did that answer your questions? And like I said, unfortunately, I don't have those numbers right on the top of my head. But yeah, with the questions, y'all nailed it. The fungus is really, really important. And we know if we don't have soil health, if we have compaction, if we have those waterlogged conditions, if we have wacky chemistry, right? If we have nutrient enrichment, particularly with phosphorus, if our pH isn't right, we're not going to create a habitat suitable for those very, very beneficial fungi. And we're not going to see that nutrient acquisition as efficient as we would as if it was there.
Great. Thank you, Jamie.
You betcha. Thank you. So Rue was all excited about these pictures. So this is what I spend my days, right? Standing in soil pits. So I know you have unmute buttons. So here's a picture. What do y'all see? I can tell you I was up in Marinette County. This is up by the UP. This is a conventionally managed field. What do y'all see? Obviously, I was really excited. I took a picture.
I don't know what I see, Jamie, but I can say it, like the top looks like soil, but then the bottom half looks more like a rock outcropping.
Perfect.
Rufus, come on.
What
I
do you
see
got,
your hand
Rufus?
up.
Yeah, I see some pretty heavy clay
Yes, sir.
on the bottom there, and then that slow transition into some sort of topsoil. It seems pretty compact.
It is. So actually Claire gave the usual answer, right? It's like, oh my goodness, it's just topsoil over rock. And I wish it was, because it's actually topsoil over soil. So this is a conventionally managed system. And what you're looking at is a plow pan. So that is one of the worst plow pans that I've seen in a heavy textured soil. You'll notice, so we have this beautiful high organic matter soil. You'll notice it's fairly well aggregated. You see that cookie crumb structure, we'll call it granular structure, that tiny little ball structure that we want to see in most soils that promotes porosity. So that topsoil doesn't look so bad. But as soon as we get below that, you'll see that heavily compacted area. You'll see those roots. They're trying really hard to get down through that layer. But they're not doing a very good job of it. They're kind of stuck. So there's a whole lot more roots in that upper A horizon than there are in that plow pan and even into the subsoil. So when I talk about a nutrient acquisition issue, right? When I talk about water access issue, this is a huge problem for us. And this is not uncommon to get into a soil and see this kind of compaction. Realize that this kind of compaction at this depth, this is about 6, 8, 10, 12 inches, right? So that's probably, looks like at least it's probably about a 4-inch layer right there. Realize that compaction is very, very difficult to get rid of. And so biologically, research has shown from Penn State, biologically, if we should expect that compaction to be there for the next 2, 3, 4 decades, right? Or more. And I can tell you a secret of a soil scientist is that I can get into a soil pit, and if soil pit has been moldboard plowed, 40, 50, 60 years ago, and it's been converted to no-till after that, I can still see evidence of that moldboard plowing, because that lower subsoil compaction takes a while to get rid of. Roots do a great job. Freeze thaw does not. We all think that freeze thaw gets down there and breaks that up. It doesn't. Freeze thaw only really works in the upper couple inches, but we have to wait for Mother Nature, wet, dry, earthworms. We have to wait for roots to take care of that for us. So this is a huge, huge issue, not only for productivity, but for nutrient acquisition. And that's why I threw it in as a picture. I can manage that fertility all I want, but that's not the issue. The issue is that plow pan in the center. I see some things coming into the chat here. All right, so what are your favorite tools for fighting compaction? I love that question. Don't have it in the first place. So isn't that a terrible answer? This is where I always make a joke, right? So is if I could teach farmers in Wisconsin, so up here, so, we're the cheese state, we're also the beer state, right? So if I could teach farmers how to drink beer and play cards, I could fix compaction in the state of Wisconsin. So that's all it takes, as I need to teach people to play cards and drink beer. Why is that? Why is that my solution? Rufus is laughing. So I can only see you. Sorry, Rufus. You, Claire, and Rue is all that I can see. So let me see if I can see everybody else. Change my view. All right. Why? Compaction comes when most of the soils are going to compact, mostly when the soils are wet, right? So it's not when they're saturated. Saturated soils are actually very hard to compact because the water is providing that soil some strength, right? So when you walk across it, you drive across it, you're trying to compress that soil, or you're compressing the soil as you do that, as you drive or you walk across it or as you work it, right? But because it's saturated, that water is helping to hold that implement up, is helping to support some of the weight. Maximum compaction happens when the soils are about at field capacity. So when the soils have stopped draining, right? So by definition, 3 days after saturating rain, when that soil has just enough water, it's very moist, but that water, instead of helping to hold the soil up and provide some strength as we move across that soil, is actually acting as a lubricant, and it allows those soil particles to move back and forth. So you get a soil you get a soil in this picture here by manipulating the soil, by harvesting, by planting, by tilling, by driving across it when it's moist. So that's how you do this. And so if we could just be a little more patient with our field operations and only go in when those soil conditions are optimum. When is that? Is when I don't see lug marks, when I don't see feet marks in that field, when the soil is dry enough that it can support us. If I had to fight compaction, and this is where I am not opposed to putting steel in the ground, right? And actually that was my recommendation for this field, right? So I walked across, I used my penetrometer, I verified that I had this plow pan throughout the field. I verified where the depth to the top of it is, where the bottom of it is. And then we went in and we used a ripper. So we deep ripped this field. With when the soil was at a proper moisture content and with the proper settings. So I want my sweeps, I want my shanks at least 2 inches below the depth of this plow pan. And the reason for that is how a deep ripper works is it basically picks that dry soil up and it drops it. And when it drops it, it shatters that soil and it starts to create those fracture planes. Please realize when you do this, all you're doing is moving the compaction lower. But what we're doing is we're increasing the rooting depth at that point in time. And Jamie Patton's rules are if we deep rip, it is immediately, and that's a capital I, immediately followed by a cover crop. So if I'm creating, or a crop, if I'm creating those fracture planes, I want them to be held open by roots. So I don't want them to settle back in. So if I'm going to spend that diesel fuel on that time and that wear and tear on that equipment, I want it to work. And so it has to be immediately followed by a root system. Dylan.
Yeah, that was super great. And I'm wondering if we can go even deeper on that topic and you can give us some more real nerdy details about deep ripping. So like width of sweeps, do you ever take off the sweeps and just use straight knives? What type of cover crop?
And we'll get to the cover crops later on. I have a beautiful picture of rooting systems. I could talk for days about how much I like the rooting systems of certain cover crops. So yeah, oftentimes I'm more of a sweep, and it really depends upon, and I can't give you an exact answer, Dylan, because what we're going to be talking about is different soil textures. So our sands are going to react different than our clays, right? Versus the silt loams, depending upon where you're at in the state. So we're going to be looking at that area and making sure. Shanks oftentimes will work, but I'm going to have to place them fairly close together. And what that does is it increases the amount of draft that I need in order to get through that field. So now we're talking about energy requirements and tractor size and so on or so forth. Yeah, so I do like a sweep. That would get us off into an engineering property. And actually, this is where you talk to ag engineers. So if you really want to get nerdy, don't talk to the soils gal. Talk to the engineers, and ours is Brian Luck, and he'll do a great job of helping set that up for you. But wouldn't that, Catherine posted, and wouldn't that be tilling? Yes, it's tilling. So the challenge here is when we look at this plow pan right here, this is yield reduction, and huge yield reductions. In fact, that day, when I took this picture, they got about a 1/4 inch of rain, and it wouldn't infiltrate that soil. The surface was completely muddy. My boots were covered in mud, and they were about 5 times bigger than they should have been when I walked through that field, but the soil's dry down below because the water simply can't get in. So at this point, biology, and at this severity of compaction, in my lifetime, biology is not going to help me enough to overcome that to overcome the yield reductions from I see here. So in this very instant, like I said, you'll notice I'm using very specific terms. I walked the field. I verified the plow pan was there. It was consistent across the field. I verified top. I verified bottom. I made sure I met all my requirements. So because I am going in there with a disturbance, it is going to have the highest probability of working, and then I'm never going to do it again. Like I said, I don't advocate people buying deep rippers. You rent them from your neighbor if you need one, and then you let him or her have it. And you then follow up with a management system that maximizes reaggregation of the system. But biology isn't going to help me in the short enough term to maintain yield here. Dylan.
I'm sorry to keep hammering on this point. I'm sorry to everybody else who's just been considering buying a deep ripper, and I'm really curious about this because I see a lot of no-till growers, or also people looking at these keyline plows, like using them maybe without sweeps more often, and so you're saying do this once and never again in your lifetime. But I've seen people talk about. Especially on the permanent bed systems where they're not tilling, to regularly use just a straight knife to deep rip to provide just that vertical tillage. I mean, I think what most of us are concerned about is the inversion, not like having any steel in the ground at all.
Right.
But, yeah.
And so in that instance, a straight shank is going to be probably what you want to achieve rather than a sweep. So in this instance, I wanted a sweep because I needed to pick this up and shatter it because I don't want it to be done again, because we're in a conversion, hopefully to no-till. This is where we're working with this farm. But yeah, you and I can chat offline later on and really get about this. But yeah, in that instance, a straight line shank will help us with some of that vertical fracturing. And may be helpful, but we really do want to, if we can, change the system that we're in so that we can move away from that process. If we can, and if we can't, then we're going to work on building soil health. And so this is the instance when we talk about no-till, and the exciting things about building soil health is that they're resilient, right? And I was talking with someone today about they had to use a fungicide in their field, and they were very upset about that and how it was going to set back their fungal communities. And he and I talked a lot about resiliency, right? So when we build soil health, right? That soil, what I mean by becoming resilient. So as we build soil health, in this instance, for example, with the example of a fungus, right? As I build soil health, I'm building that fungal population. I'm building that fungal population. I'm bringing in diversity, I'm bringing in number, right? And when I do that, I develop these beautiful populations of fungi. So if I do have to come in and use something that's going to set that population back, right? It maybe started here, but now it's here. So if I set it back, it's not going to set it back to here, right? It sets it back to here, right? And it's going to be a short time, right? Hopefully, if it's a resilient system, it bounces back quickly to where I was at before. And then I can continue on my journey, right? If I don't have a soil health system and I have a minimum amount of fungi, in this example, a minimum amount of fungi, and I set them back, I might set them back close to, we'll say close to zero. And it's going to take forever, quote unquote, for them to rebuild back, because that's not a resilient system. So this is the whole idea with soil health is we do the best we can, right? And we build those communities, we build this health, we build this resiliency in our soil. And when Mother Nature plays against us, and we might need to come in and use a management tool that we wouldn't normally, we need to recognize that we're not setting that system back to zero, right? We're setting it back, but because of now that it's a stronger, healthier, more viable system, it'll bounce back more quickly. Does that make any sense? All right. I see Rufus and Rue nodding their heads. Like I said, they're the only two I can see. All right. All right. Let me show you another picture of a soil. Man, so I just need to put a whole PowerPoint of pictures of soils and we just talk from there. I mean, who actually wants words? Because I mean, we saw this one. This one is really ugly. This made me want to cry that day. This made me want to puke. All right. So what do we see here? This is why I argue that we can't use straight up organic matter as a soil health test, because this soil is really high in organic matter. Look how dark it is. If I just looked at organic matter, this would be fine. But this soil is not healthy. Muck. Great job, Thomas. No, it's not. Unfortunately, it's not. This is a mineral soil. So this is primarily sand, silt, and clay. So, but what do you
Very
notice?
unstructured.
Oh my goodness, you have that correct. This was the only soil pit I've ever been able to jump into, and I actually picked the entire topsoil up and I held it like this as one big chunk as I talked from the bottom of the pit. This soil has no structure, right? And you can see that from the root systems. How do we know we have no structure and our roots are having problems of nutrient acquisition? Look at these. All right. So this is another sign of compaction. This is obviously, you can see this here. We don't see, it's just one consolidated block mass. If you were, like I said, if you were an earthworm, would you want to live here? Where would you go? And how long would it take you to get there? It's terrible, right? If you were a root system, where would you go? And how much energy would you have to put into getting there to burrow down, drill down through this soil? And when you look at root systems that in highly compacted soils, this is what you see. So I'm moving your pictures around. So let's look at the left-hand side. What do you see there? I see roots that are doing this. Sorry, my chair almost fell over. They're like plastered against the ped, right? They're plastered against that aggregate. They're flat. Whenever you see flat roots, roots aren't supposed to be flat, right? So that soil was so compact, that root was finding any fracture plane it could to try and grow down through that soil. It grew flat through a crack, right? And they're all compacted like a cell tray plug. They do that, right? So whenever they hit the sides, right, they grow flat and they all proliferate right there because there's a little bit of air, they're able to get a little bit of water. You don't see any root hairs at all in that side. When you look at the right-hand side, you see the same thing. There's a huge root system over there, but it's flat, right? And it's not going anywhere. So these are the things when we talk about soil fertility. Everybody likes to talk about soil testing and adding fertilizers, and I'm the weird one out here screaming, let's look at your compaction. Do you have big, beautiful root systems? Do you have fungus? Because if you have something that looks like this is our problem. And this is what we need to address first. And when we think about increasing productivity. So John, did you have a question? I see you popped into my screen. Nope, just smiling. All right. But questions? So when we talk about assessing soil health, I'm a huge proponent. If you'll notice, obviously, I think the most important tool we can use to assess soil health are right here, right? So this is the tool I use. I use a shovel, my hands and my eyes. I observe, right? Because I can see, right? This isn't working. I can see that there's an issue, and I can see there's a management change I can make to make that soil look something more like this, right? So this is my soil health soil from the state of Wisconsin, right? So it's not a thick, dark, black prairie soil of the South, right? This is what a big, beautiful, gorgeous, healthy soil might, in an agricultural system, might look like in northern Wisconsin, right? It's brown, right? I realize that, but we don't have as much organic matter in the soils up here, right? We're old forests. But what do you notice about this as compared to the other pictures I've shown? We see that root system. Notice how fine it is. Notice how long, notice how it's everywhere. In this picture, you'll see that little bit of a cover crop on the soil surface. This root system is everywhere in the soil. And when you look at the soil, can you imagine picking it up and it just crumbling in your fingers? How soft it would feel, right? That it would just, like, I don't want to say melt like butter, but it would crumble, right? Like cookie crumbs in your fingers. You can see that from this picture. This is what we talk about in soil health. And this is what we talk about with nutrient acquisition. To me, this is one of, along with pH, is the primary factors we start with when we manage soil fertility, we manage soil health. If you want to cycle nutrients back into the system, you have to have a soil that looks like this or darker, like I said, depending upon where you're at in the state, but you have to have that root system. You have to have that structure. You have to have that biological activity to manage that fertility. And that's where I fall asleep at night thinking how beautiful this soil is, right? You can imagine, obviously I think a lot about it, right? Because I can even, as I describe how I think it feels in my hands, right? That's what a soil is like. So let's get deeper into that management. So Dylan wanted to talk plant roots. So these are some of the questions that Ruth sent me that you may have. So, and if you have more, throw them in. So one of them was, can plants use surface applied nutrients? So what do we think our answer is? Look at all these people I didn't see there before. Wow, so I rearranged my screen. There's a lot of quiet people out there.
I would guess yes, but not as efficiently as if they're incorporated.
And it depends. So obviously, so the question is do I have root systems near the soil surface? And so I really like this graphic, and I realize these aren't necessarily crops, these are cover crops, but you'll see them at the bottom of the screen. And I borrowed this from the Indiana Conservation Cropping System Coalition. And I love to look at this picture, right? And it actually has a scale. If you can see it, it's very, very small, I know, but it's on the left-hand side. It goes from 0 to 60 inches. So it's 0 to 5 feet. And so when we look at many of those root systems, you'll notice that they're not necessarily at the soil surface, right? They are slightly below the soil surface. We know that 90% of all roots are primarily in most crops, and most plants are within the top 6 inches. So they aren't going, so surface applied nutrients oftentimes, if they are truly on the surface, aren't going to be available to many of these plants. But please realize that when we amend them, right, they're going to dissolve and they're going to move in to the soil. They're going to move down into that rooting zone. we have our helpers out there that help them move into the soil, right? So they're going to move in with that biological activity. So whether it be earthworms, whether it be our mites, whether it be all those little critters that we don't pay any attention to, are helping to move those nutrients down into the soil. Rain is helping to move them down. As that organic matter decomposes, they move down. So we know that we oftentimes will get nutrient stratification in some no-till systems and reduced tillage systems. So we get a higher concentration nutrient at the soil surface than we do in the subsurface. But oftentimes, if this is our system, this is how we're going to be applying our nutrients. And the key here is to figure out how to maximize bioturbation. How do we maximize biology to help us move that nutrient into the system? And how do we maximize that biology of that plant, that symbiotic fungus that y'all were talking about, to bring them into the system? So Claire came on, did you wanted to add to that? No. Are there better application methods from a nutrient loss standpoint and a nutrient utilization standpoint? If we have an option to ban those nutrients or get them underneath the soil surface, in many instances, that is a quote unquote better application method if we have the technology to do that, right? So getting that nitrogen underneath the ground, right, will help to not only reduce potential loss via runoff, but it will reduce the potential loss via volatilization, by gaseous losses. Plus it gets it down into the root zone so that the microbes and the plants can use it. Banning of phosphorus, potassium of those microbes will get them into that quote unquote hot zone where our biology can use it. But if we don't have those technologies to ban or subsurface apply those nutrients, we're going to be using surface applications, and biology can help us move those in. We are going to be very wary and pay attention to stratification, right? It says, so the next question, and we'll kind of combine these together, is there a soil testing method? And so oftentimes what I ask folks to do is to soil sample differently, right? So in the state of Wisconsin, we're required to take a 0 to 6 or 7 inch depth, whatever your tillage depth is. And we send that into the testing lab and get our recommendations. So that's the general soil sample that we always talk about. In a no-till system or a reduced till system, what I like to recommend is to not only take that 0 to 6 inch sample, but also take a 0 to 2, and we're going to keep them separate. So that composited 0 to 2 inch sample, I'm going to have analyzed as well. So this way, what I can do is I can monitor, right? That I see, you can't see that. I'm going to monitor the concentration at the very surface, as well as through that root zone. And if I do get that nutrient stratification, now I'm going to be thinking about ways in which I can either change up I can somehow get those incorporated, change the biology to make that happen, or I'm going to be looking at subsurface banding methods or something along those lines. But more importantly, in a no-till system, we have to be very careful in managing that pH. So when we apply many of these amendments, right, we may be acidifying that surface. And since we aren't going, if we want to maintain a no-till system, we're not going to be able to incorporate that lime. So the recommendation from UW is to take that 0 to 2 inch sample and that 0 to 6 inch sample. And as soon as that 0 to 2 inch sample gets less or 2/10 or more than 2/10 of a unit below the pH for our target. So if I want to maintain my pH at 6.5, I would take that 0 to 2 inch sample. And as soon as it got to a pH of 6.3, then I would consider applying a ton of surface applied lime to bring that pH back up. So my tolerance level in a no-till system, particularly if your pH is going to be less, because I don't have the option of incorporating the lime to change that pH throughout. So I'm going to be more aggressive at managing that pH in that surface. And by doing that, hopefully then, like I said, we can promote biology and we can promote nutrient availability within that system. So questions, comments, we attack those three. Let's see, there's a comment in the chat. Sorry, I need to get new bifocals, so I had to sit back in order to read your comment here. So often we see no-till vegetable farms with a lot of organic matter due to heavy compost applications and a high pH. the standard recommendation is sulfur, but is it effective on very high pH soil, very high organic matter soils with a high buffering capacity? And do you have any alternatives you can suggest? No. So that was an easy answer. Sorry, I'll expand on that. So no, the challenge is whenever we have high pH systems, right? Excuse me, high CEC systems, high organic matter systems, they are very, very buffered against change, and particularly that high pH. So in order to bring that pH down, I have to create acid into the system in order to utilize and basically neutralize all that carbonate in that system. Sulfur is the one we recommend, but it's in highly buffered systems, it's never very effective. On a small scale, you may be able to keep up with it. So blueberry production, for example, up in my neck of the woods, we can, in very small areas, we can amend to keep that pH where we need it to be. But it's very, very difficult to acidify soils in a buffered system. Anybody agree, disagree, or have ideas? Rufus, did you want to, is your hand raised on that question or that comment? No, we're looking at everybody else. So now we're crowdsourcing answers to how do we lower pH in a high organic matter, high pH system. How do we get that done? Because I don't have any answers.
We tried, but well, actually, no, we didn't actually end up adding the sulfur, but that was the recommendation in our high, because we were experiencing some issues. My question was related to research for some sort of biology that is more aggressive in pulling those nutrients down. Are people finding particular no.
No, and this is where the caveat. So I want to go back to that other question. So unfortunately, I'll just finish that up. Unfortunately, my answer was going to be sulfur. And as we know that, so I'm not giving you an answer that we're looking at. So I think most of us are probably using neutral and moderate alkyl nutrient sources. So, but I use sulfur and curious what others. So let me read that more quickly because that was to someone else. So Dylan asked, I think most of us are probably using neutral to moderately alkaline nutrient sources like you used an acronym on me.
Composted poultry manure.
There we
CPM.
go.
Yeah.
Perfect. Composted poultry manure. Yeah, I just put some of that in a nutrient management plan the other night. And feather meal. So
yeah, Jamie, that was my nutrient management plan.
Hey, Dylan. Hey, all right. You're from Crawford County. All right, we did you. Perfect. All right. So what is everybody? So, and I use sulfur, but anybody else? Like I said, and Dylan, I'm coming back from the conventional world. So I work with soils in the Northeast. The highest I've ever seen is 8.6. And so the challenge is maintaining micronutrient availability in 8.6. And we never think about lowering the pH because that's not a viable option. I'm looking instead at managing micronutrients in a different way in that system. So keeping them away from the soil. So this is oftentimes if we have the option for a foliar application of those micronutrients, if you have options, that's a way to get around some of the nutrient unavailability in those high pH soils. It's more viable in high value production systems than in my conventional systems. But from an effectiveness standpoint, I can't bring the pH down. So I find other management techniques in order to improve nutrient availability. So all right. Is foliar only mildly effective? Yeah, this is where it is, but we have no other option at this point. So unless somebody else wants to chime in. See, I'll do this more than I do. I just sit in the Radisson and chat with you. I don't actually farm. So
Well,
Oh, go ahead.
go ahead, Desmond. You got your hand up.
Well, I was going to say, and this is something I've been trying to do. I haven't necessarily don't have any results to speak about. But our pH is rather high. It's not crazy high. But it's mostly due to an excess of magnesium, I think. And so I'm using a lot of gypsum to try to slowly replace magnesium with the calcium and then have the sulfur wash that magnesium out. And just kind of hoping that that will bring our pH down a little bit. I'm actually doing it more for the calcium boost than or for the soil structure more so than for the pH change. But gypsum is a neutral pH change, but it should help remove some magnesium from the soil, is what I've been led to believe at any rate.
Right. And so, but it's not really going to change your pH. And so in order to change the pH, we have to take out the neutralizing ability. So we need to be taking out that carbonate portion. And so that's where it's not an issue. I need to somehow basically add an acid, and this is what we're doing. In order to neutralize that carbonate, which is naturally occurring in our system, I need to add an acid. I need to eat it. It's a hydrogen, basically. So basically, I need to take that carbonate and I need to convert it into carbon dioxide and water. So think about making volcanoes, right? So this is the easiest way to explain it, right? So think about sodium bicarbonate, right? Baking soda and acetic acid, right? When you add those two together, right, you get water and you get carbon dioxide, and the pH changes, right? That it goes down because you no longer have as much carbonate in the system. All right. So, and the OH ions basically. So this is where chemistry is a challenge to describe when you're in online. So pH, right? It's either hydrogen ions or hydroxyl ions, OH ions. I have to get rid of these OHs, right? The problem is the OHs is the base, right? So when you think about water, it splits. We get a hydrogen and we get an OH ion, a hydroxyl ion, right? So in a high pH system, we have too many hydroxyls, the OH systems. I have to get rid of this OH. Right. And the way I do that is I add acid into the system, which is the hydrogen. So if I add hydrogen, the hydrogen reacts with this OH ion. I no longer have the hydroxyl. Instead, H and OH combine to form water, right? And it turns neutral. And so we don't have that high pH system. I no longer have an acid and I no longer have a base, right? So when we add calcium into the system, right, that calcium doesn't do anything to this OH over here. It stays as an OH. And therefore that pH doesn't change. I have to add acids into the system to convert this OH into a water. And so this is where it becomes problematic and the chemistry doesn't work. And why I said carbonate, because what carbonate does is it helps to neutralize a system. So rather than the acid coming in, right, this is why your pH doesn't change. So instead of the acid coming in, and the H ion coming in and reacting with this OH and converting over to water, and the hydrogen comes in, right? But instead of reacting with the OH, it reacts with the carbonate over here, and you get carbon dioxide in water, but you still have the OH and the pH doesn't change. Okay. If that makes any sense. I wish I had a diagram on a whiteboard, right? So in order to change the pH, you have to get rid of this OH. But in order to get rid of this OH, you have to get rid of the carbonate, which is buffering it beforehand. And this is why you have to add ungodly amounts of sulfur, right? Because I have to get rid of this carbonate, but I also have to get rid of this OH. I have to add enough acid, and that sulfur produces acid to get rid of both of these things in order to get the pH to change. No, I know. Chemistry online sucks. And hands go up. Tenzin. Mr. Botsford. This is Botsford. I guess I don't know.
I think Tenzin's hand might still be up from before,
Okay.
but
Yeah,
Natalie
sorry,
also...
it was still up from before. I'm not actually sure how to put it down.
Yeah, I was gonna say, yeah, and he's just dumbfounded. He's like, woman, that is the worst answer to it. That's the worst answer to a question I've ever heard. That was so confusing. So
No, I think it makes a lot of sense. I was really just running it by you to see if my understanding was even close to accurate. And like I say, I'm not doing it necessarily for the pH reduction. I was told that might happen as a side effect.
maybe, but probably not. I like
Okay.
I like gypsum. I use it a lot as a sulfur amendment. So,
Mhm.
all right, Natalie, and then I'll get back to Rufus's answers about super biology. So I haven't forgotten about you over there.
All right, thanks. I just have a clarifying question. So,
Yes.
like the pH of your soil is related to the carbonate that's there, but my understanding was that like as we're adding a lot of salts to the soil, which can happen in like decomposed mulch systems, that affects the alkalinity, which then also has an effect on pH. Is that accurate? So part of it is like washing the salts out, right? In addition to all the chemistry that you just explained.
I was not ready to do this much chemistry tonight. So yes, so what happens is, so what's really fun about this system is the soil has to maintain electroneutrality. So when you add compost, such as these things that are nutrient rich, realize when we use the word salt by definition can be a lot of different things. So nitrates are salts, sulfates are salts, chlorides are salts. So all of these are salts. So don't just think sodium chloride, potassium chloride. It's gypsum as well. So many of the fertilizers that we add, if they dissolve readily in water and contain a metal, are salts. So what happens is the soil has to maintain electroneutrality, meaning that we can't just keep adding charges in. We can't just keep adding nutrients in, particularly positives and negatives. It's going to have to get rid of some at some point in time. And that's how we end up with leaching, right? We end up with nitrates in our groundwater. We end up with hard water because the calcium and magnesium has moved out of our soils and has moved into our groundwater. It's why the ocean is salty, right? Because we added so many things to our soil and it had to get rid of some things. So they washed out into the rivers and they end up in the ocean kind of thing. So yeah, this is where all of these statements you are making are true. It's just to the extent as to what impact they have on pH. So as we wash things out of the system, we have the potential to wash some of those carbonates out of the system. We have potential to wash things out of the system, which will change my pH. As the realize, and as you add these beautiful composts and these manures and these organics and the feather meals to the soil, as they break down, they create organic acids, right? So the microbes are creating that and they help to consume and get rid of some of these carbonates, which are buffering the system and are keeping that pH high. So it's extremely complex on how this all works, but yeah, it is. Over time, the soils will naturally become more acidic due to the production of acids by the microbes, by the interactions of carbonates. So as microbes and plants breathe, that carbon dioxide goes into the water and it produces carbonic acid, which then neutralizes some of that alkalinity. We get the addition of nutrients. We get the uptake of nutrients by plants, which create it. We get the leaching of nutrients by plants, which creates more acidity. This is why I've studied soil for, God, I'm old now, 30 some years, and I still don't know very much because it's very complex and integrated and so dynamic on how this all works. So yes, adding some of these amendments over time, such as the compost, will help to get rid of the alkalinity, but it's just the extent to which it does that and whether or not it induces a pH change is the real question. Anybody want to disagree with me? Please, somebody else can chat. Jamie, you're full of it. That is the wrong answer.
So in our particular situation, when we went into our first year of the deep compost system, and we just dumped a bunch of compost on the ground and mostly had beautiful results. But then we had a couple of those beds that were showing like we had some bean beds that were really yellowing. And so then I did my soil sample and soil test. And of course came back super high pH. And that's when they were like, well, you could have put some sulfur on there. And I decided not to do that. And it seemed like it just came down to time, love, and tenderness. Right? It just took time. Like by next year, and I haven't returned, and done a soil sample, which I should probably do that next year, soil test. But by year 2, the crops look great. So we just kind of endured that loss of that bed.
Right. So as that organic breaks down, and as Natalie pointed out, as some of these things move and leach out, pHs will change over time. And so thinking about where those manures come from. So oftentimes, maybe for example, people don't think about this, but that it can have an impact, right? So if these animals, if you're scraping manure off a concrete lot, right? So for some reason, the animals are on concrete, it's a lot, you're scraping it off, you end up with carbonate, you end up with extra lime in that manure, right? And so it will change the pH, it acts like a liming agent. I work with a lot of dairy manure, right? So we bring them into the parlor, and what do is we lime the walkway, right? So that nobody slips while they're in the parlor, right? So we use barn lime, right? Also help to control some odor. So it's lime that we don't think about, that we're adding into a system that ends up in that manure when I clean the parlor, and it's going to be a high pH type manure. So there's things that are coming into the system, and I never, like I said, it's really hard. And I like your answer, Rufus, of not that we need to wait it out, but we can get into this cycle of, I have this challenge, so I fix it with this, but then I use this, and then I end up with this challenge, so I have to do that. And we just end up in this pendulum going back and forth, trying to fix an issue when, small changes, small tweaks, and in this instance, a little patience, right, fixed your problem for you.
Well, I think it also highlighted to me too that it's really important to have that compost aged.
Mm-hmm.
So, because that's just a natural process. Right? The pH just naturally lowers over time.
Yep, as things leach out, and we get rid of that potential immobilization or tie up of those nutrients if that compost is fully stable and it doesn't want to break down much more. We don't get that tie up event and that yellowing of crops early on. Because the microbes aren't using our nitrogen, it's still available to those plants. So let me go to chat here. Actually, yeah, Rufus and others using deep compost systems. Are you requesting compost analyses from your sources before buying?
So we, so far, have, besides the stuff we've produced ourselves, we've purchased from Purple Cow, and they do have analysis. I think it's general though. I mean, I don't think it's per batch. I haven't, I guess I should say I haven't requested per batch yet, but I did, after I took the soil sample, I did get on the phone with them and kind of had an extensive conversation with them, and that was kind of what came from it, is that, it was still pretty, a lot of these bigger operations, they're moving that compost out pretty fast. They're basically adhering to the minimum standards of time, and so you're getting loads that are pretty hot, and especially later in the year, as you go into the summer. So their recommendation was maybe doing, getting something in the fall and letting it sit over winter.
Yeah, that's a good point. That's interesting. I wonder if Cosmo or other like larger regional providers are any different. Can't imagine they are, really.
So one other thing too that kind of came to mind after, because watching a bunch of other videos, there's a lot of other things or reasons why you probably want to get a detailed analysis. What's the forever chemicals that are kind of showing up in some of these things?
PFAS.
Yeah. So, but we're kind of moving more towards our own on-farm stuff. So hopefully we don't have to buy much more. Not that it was great. It's great, but it's just too young. That's the biggest thing. at least in my opinion so far.
Rufus, I had a question, and this is kind of general for anyone using deep compost mulch systems. How, I know you talked about this, but I forget what depth of compost you're putting on, and I'm asking mainly because I'm curious how much you're seeing plants' root systems in the compost versus in the soil, because that's going to obviously impact where they're getting their nutrients from and how you might interpret a soil test versus your compost analysis.
So in the method that I adopted, we went directly on top of our lawn, basically, and put 12 inches of just pure compost on top of our lawn. So as far as my plant depth, I have basically it's growing in the compost. It's not in it's not going down into the lawn from what I can tell.
Yeah.
Although certain sections, I think now that I think about it, this summer I was noticing there's a little bit more of the original soil that seems to be coming up as I'm pulling up a plant root. So it's in certain places, but it's mostly 100% compost.
Mm-hmm. Yeah, so having that really matured compost is like certainly early in their growth. Regardless, they're going to be just in the compost because they're tiny plants. But
yeah,
it sounds like for most of their life cycle, that's where they're getting the majority of their nutrients.
Yeah, and my intention is to keep on adding to. So I'm basically like, I imagine it like I've got that hard pan of the the lawn that's down there, and at some point, like when I'm an old fart, it's going to be like 2 feet down, or I don't know, maybe more, 3 feet, 4 feet. It's gonna be way down there. My bed's gonna be way up here, and it's just gonna be thick, beautiful compost. That's my dream, I guess.
I'm excited that you're making your own compost too, and I think as you like go on with that, it's interesting to think about how much you can kind of tweak your recipes and even amend compost to get a nice balanced mix.
Yeah, I'm personally really excited about it. I mean, I've been in the oh shoot, now I'm forgetting the acronym, but because I haven't taken any of the classes in the last 6 months, but Elaine Ingham's soil course. I'm in that course right now, and so I'm still in the middle stages of that course. But there's another gentleman in our area here who finished that course, and we've been working together on taking biological samples of our soil. And he's in the training phase of that too. So we're kind of like learning together, but it's absolutely fascinating. It's a lot of fun. And so yeah, we're just like little infants on it right now, but having a lot of fun doing it. So yeah. So basically too, the other thing too I was thinking is I'm hoping to get this set up this winter where we've got a bunch of Amish in this area that have a lot of sawmills. So I'm hoping to start collecting, because based on what this other gentleman is telling me, like the adding the wood chip carbon stuff is the fastest way to get your fungal levels way up there. And so the samples that we've taken so far of my compost, and then all the different several of the different garden plots, there's not a ton of fungal life in there yet. So, but he's also new at it too. So he's like, he's not quite sure. There might be more there than he can identify because he's not quite sure yet of all the different varieties. But, and then fascinatingly enough, we have a bunch of hazelnuts out here too that we did a sample of. And he was really surprised to see that they were really low in fungal activity. But of course, this is our old regular conventional farm fields. So, but it hasn't been that way for 10 years, but there's still not a lot of fungus in there yet. So hopefully I get to play around with it for a while, and we'll see.
Very good. I'm just gonna run through the chat as we're pushing up against time. So yes, the acidifying of irrigation water. It says, does rainwater tend to be acidic? Yes, natural water tends to be around a pH of 5.5. So as we increase air pollution, that pH goes down. So that's also one of the reasons why soil pHs, pH in general tend to decrease over time, is we're adding acids through that rainwater. So crazy amounts of sulfur. All right. Nice. I love air pollution. No. So no. We wouldn't be applying sulfur. So Clean Air Act of 1970 has done wonders, but not for sulfur fertility. That's one of the reasons why you need sulfur more than you did back in 1970 for some of you who were alive back then. So no, wonderful. Absolutely fantastic discussions. And like I said, I love that that you're all having fun doing that, because otherwise it's just a job. So this is why we do all of this. And I apologize. Like I said, you took me down. This is fantastic. You took me down some roads I wasn't expecting to go down. Who knew pH was going to be the hot topic tonight? I was hoping I got to talk about soil aggregates, because that's my favorite thing to talk about. So maybe some other time, but
you know, I don't know if you have more slides to go through, Jamie, so I was kind of holding off.
No, you're good.
I know Dylan, like since you mentioned soil aggregates, Dylan said something about tillage radish in an earlier comment, and I have been so curious about tillage radish. I've never really used it myself, but you know, I have done a lot of research on potatoes over the years, and in situations where, you know, people are moldboard plowing in the spring with the aim to like get a deep planting bed, but then at harvest we just have these terrible plow pans and big chunks of soil coming up, and this is actually what got me personally interested in reduced tillage systems, because I was working with potatoes so much and I was seeing the impact of that on the soil, and just getting really curious about how you could ameliorate that. Like if you're in a system where you have potatoes coming through that system or other root crops coming through that system, you know, maybe every 4 or 5 years, how much can you try to improve soil health in the meantime? So that's a little bit of a digression, but I am curious about the use of tillage radish to try to fix a situation like that, whether it's something that you include in a rotation or something that you do to try to fix a situation. And then, like you were saying, the best way to ameliorate, or the best way to fix compaction, is to not have it in the first place.
Right. No, and that's a fantastic question, Rue. And that's where I'll put the screen share back up. This is why this picture of roots are on here. So this is where, when you look at, let me minimize you all so I could see my screen here. These are our typically used cover crop roots. And I will point out, so tillage radishes are in the daikon radish group. So you'll see them there as the 1, 2, 3, 4, 5, 6. It is the 7th plant. Excuse me, I can't count tonight. It is the 6th plant from the left. And so when you look at that root system, right, there's the oilseed radish and then there's the daikon radish. So when we think about creating aggregation, it's about, and creating pore channels, it's about roots, and more roots. So the challenge with using tillage radishes is I have found everybody gets really excited about that large root at the soil surface, but in all reality, it's not doing really anything for me. It's creating a big, gigantic hole in the ground. And those roots that are supposed to go down and oftentimes tap that plow pan don't. They stop at the plow pan and go sideways. So while we really like tillage radish, it's a really good marketing tool. In all reality, let's look at the rest of these cover crops. So if we want to think about, you know, they do go deep. So the oilseed radish do that too. Canola will do, rapeseed will do that. A lot of the brassicas have that deep kind of taproot system, but I will ask y'all, what is the challenge with using a brassica? Right? There's always trade-offs in agriculture. There's positives and there's negatives. So what's one of the negatives of using a brassica, such as these radish, these turnips, these rape seeds, so on and so forth. All right. There, Dylan gave me the death sign for black rot, but no fungal symbiosis. So that's what I always want to point out is so you may be poking holes, but have you ever, and this is where I encourage you, if you've never worked with cover crops, to go out and go into somebody's field, just stop. So I'm allowing you to trespass, right? And start pulling their cover crops out of the ground. Right. And what you'll always find, and somebody pointed this out to me, right? So if I go and I try and pull cereal rye out of the ground in the early spring, it won't, right? Because if you look at that beautiful big root system, and as it grows down, it gets really fine roots and it gets into that plow pan and it starts to break that up. Annual ryegrass is actually the cover crop on the far left. And look at that. I mean, that root system is phenomenal. It is absolutely gorgeous, right? We can love that root system. But when you go out, I encourage you to go out, and when you pull those out of the ground, right? This is what I want you to notice. When you pull the grass cover crops out of the ground, when you pull those broadleaves out of the ground and you pull those root systems, right? You'll notice that there's aggregates and chunks of soil connected to that root system, right? Because that root system is growing inside the aggregates. Plus it's inviting fungi in, and it's helping to create those aggregates. Those root systems are always dirty and full of aggregation, right? Has anyone pulled a radish out of the ground? We all have, right? Anybody ever done that? Describe what the radish looks like when you pull it out of the ground.
Big bulb.
It's a big,
One
right?
big, yeah.
And is it dirty or is it clean?
It's mostly clean.
It's clean, right? Somebody pointed that out to him, like, that is a fantastic visual, right? That radish doesn't have that mycorrhizal infection, right? It doesn't have that symbiotic relationship. It is not helping us create and bind and stabilize aggregates, right? It's not helping us create that soil that we want to see. You yank it out of the ground and it's clean. You brush it off a couple times and you eat it, right? Because there's not that much dirt stuck to it. So when we think about creating aggregation and getting rid of some of that compaction, yeah, if we like that taproot system, right? So add a little bit. And when I say a little bit, I think in acres, so apologize. I think in acres. So I'm looking at a 1/4 pound or a 1/2 pound per acre. Very small amounts, but I'm going to have a dominant system with my grasses and my legumes and things that are going to promote that fungal activity and that aggregate formation. I'm going to use some of those taproots in there and see if they can get in and break that up. But in all reality, I want roots that are going to feed my biology down there. And you can see that down there. So, that's why I love to show this picture, like I said, and is just to get us to think about it. Throwing, and this is where you'll see oftentimes we put a few sunflowers, right, in that mix. So as we've all tried to pull out a sunflower, right? I'm gonna stop sharing. Has anybody tried to pull out a sunflower from the ground? You all have. You should laugh because you can't do it. It's like a tree, right? It's a big, beautiful root system that grows. You'll notice from the picture, it was growing not only vertically, excuse me, but horizontally. It was getting up and creating that compaction. So again, if you've never seen these pictures, you can grab them from the Indiana the Conservation Cropping System Coalition, and just sit and look at them and think about how, if we want to create aggregation and how we want to break up compaction, think about how we can combine these root systems together, the benefits of each one, and how do we get a root in every nook and cranny of that soil to create that aggregation, stimulate that biology, feed that fungus. How do you get big roots and fine roots, those fine roots to get into those tiny pores and start that process of breaking that compaction apart? So like I said, obviously I'm a visual person. So yeah, looking at these pictures and really thinking about it is important. But yeah, radishes have a place, but I'm using them in small amounts for that potential drilling action, but knowing that they don't have that fungal infection and aren't helping me promote symbiotic fungi in my system. Plus if you have slugs, wow. Usually when I pull them out, I have to brush the slugs and the slug eggs off of them, depending upon where I'm at in the state. So in my sandy soils, they're always full of slugs. They're tasty to slugs. They love them. So
I know it's seed catalog season, so I feel an urge to browse through the cover crop section of the seed catalogs, even more than the vegetables that I'm usually more excited about.
And I'll be honest, so my opinion on cover crops change. Yeah, as I say, yeah,
Nice.
my opinions on cover crops change every year, because this year I've never really liked flax and phacelia. They've never really done much for me. There's not a lot of biomass to them. But oh my goodness, I was over in Manitowoc County, and what phenomenal growth this year. For some reason, right? Weird growing season. They were beautiful, and what supporters of pollinators. I mean, so yeah, really trying things out in your soils and your climate, thinking outside the box. And like I said, looking at these pictures of these root systems and just imagine how we can get biology working for us. That's what I really like. And then pick up your catalog and order your seeds early, because cover crops are hot and we're running out of seed. Every year we seem to run out of seed quick. So
Well, thank you very much for being here, Jamie. That was a lively 90 minutes, I would say.